Today, we'll briefly introduce our team project, Speech Intoxication Detection. Thanks to Professor Rita for providing guidance on our project. In this project, we investigate multiple machine learning approaches for detecting intoxicated speakers given samples of their speech. We use Surfboard and OpenSmile to extract features from the ALC dataset and leverage models from scikit-learn to classify whether the subjects are intoxicated or not. We use the alcohol language corpus as our data source. The number of recordings of the training, Def1, Def2, and test set are listed here. The original ALC dataset is unbalanced. There are more sober samples than intoxicated samples. We take advantage of an oversampling technique called SMOTE to obtain balanced training data. We also conduct data normalization to eliminate the units of measurements. Here's a diagram of the workflow. In the training phase, we extract features from the ALC dataset using the OpenSmile and the Surfboard toolbox. Then, we train and save machine learning models using scikit-learn. In the inference phase, we are able to get prediction directly for a new wave file using pre-trained models. We also provide an easy-to-use black box, where the input wave file came in and the output came out. We built 5 classification models in our experiments. The hyperparameters are listed on the slide. Here are the 41 base features we extracted from input data using Surfboard and OpenSmile toolbox. The output will be a time sequence. Among them, the best features are log-mail spectrogram, bark spectrogram, and MFCC. Then, Surfboard calculates these 26 statistical values from each of the sequence. So, for each base feature sequence, the output will be 26 statistical values. We use 4 matrices to evaluate our results: AUC, accuracy, precision, and recall. The higher this matrix value, the better the model. In order to measure the performance of different models, we construct different models for each feature, and then report the corresponding matrix value. From the results, we can see that support vector machines usually give the best results. Random forest and gradient boosting also have good results, but they are time-consuming. Then we compare the performance of different features, and here we plot the top 10. From the diagram, we can see that the log-mail spectrogram and MFCC outperform all the rest by a huge margin. We also evaluate each of the band from log-mail spectrogram. For most of the band, the result is as expected. The performance is worse than the model trained on the whole data. However, the 69th band, which range from 1900 Hz to 1975 Hz, yield even better result. We also plot the heat map of the statistical values of the 69th band. We extract 60 recordings from 2 speakers. For each speaker, the first 30 recordings are intoxicated, and the last 30 recordings are sober. Intoxicated and sober recordings are matched in order. We can see that there is a clear pattern. Intoxicated voice has higher statistical values. We further try to reduce the dimensions of this band using ICA. We gradually increase the dimension of the output. When the number of ICA components reach 15, the performance of the model reaches a peak, an accuracy of 86% and an AUC of 0.94. In all of our experiments, we achieved the best results using the model of RBF kernel SVM and the feature of log-mail spectrogram with the 69th frequency filter and ICA to 15 components. Our accuracy is about 86%, which is 15% higher than the baseline. We also get a high AUC value of 0.94. The precision and recall are both above 85%. We evaluate performance of our models against manual evaluation of speech files. We conducted an experiment of human listener manual speech detection session for testing evaluation. The results shows that the accuracy of human listener detection of intoxicated speech is around 50%. This accuracy is usually low, especially when the speech language is not the native language of human listeners. Thus, the results shows our best model that runs on the same testing set performs much better than human listeners in speech intoxication detection. The conclusion is, firstly, we build a pipeline for model training and inference. You can customize your own feature and models or make predictions using pre-trained models using a single command line. Secondly, according to our experiment results, the SVM model with RBF kernel and the log-mail spectrogram feature work best for this intoxication detection task on ALC dataset. This combination can achieve 85.8% accuracy, which is significantly higher than the baseline. Lastly, we found that a single band from the log-mail spectrogram contains enough information to train the most performant model. Thank you everyone for watching, and please feel free to contact us if you have any questions.